This self-made car is the Alphabot. My name is Philipp Schauer and I graduated from the HTL for Network Engineering at the Schulzentrum Ungargasse in 2022. And here is the result of my diploma thesis. The Alphabot was originally created as part of a free subject called Programming Workshop. After I joined the school in 2017, the development of a remote-controlled car began in the summer of 2018. Over the years, the Alphabot went through several versions. Initially, it was just a two-wheeled remote-controlled car, hence the name Alphabot 2V for two wheels. In the front, the Alphabot 2V had a ball that was supposed to roll on the ground. In fact, the ball got caught very easily in bumps. Therefore, this version of the Alphabot could only drive on flat tracks. The next development was the Alphabot 3V. This version had two wheels in the back as before, but a steerable wheel in the front instead of a ball. And the current version is the Alphabot 4V, with 4 wheels. 2 steerable wheels at the front and 2 drive wheels in the back. In addition to remote control, at some point I also started experimenting with autonomous driving. But I don't want to keep you in suspense any longer. So let's move on to my technical topics that I have been working on as part of my thesis in the school year 2021-22. I am going to talk about positioning, pathfinding, navigation, and PCB. To that end, it's worth mentioning that there are 2 variations of the Alphabot. One that uses a microcontroller called ESP32 as the main controller, and one that uses the Raspberry Pi as the main controller. The Raspberry Pi is a small computer. I was responsible for the ESP32 variant of the Alphabot, and therefore I will refer to that variant. However, I will also briefly cover parts of the Raspberry Pi variant. That is the building of a Raspberry Pi image and the Alphabot emulator. I'll start with positioning. For this, a module called DWM1000 is used together with an Arduino Pro Mini. The two are connected by a self-made adapter PCB. And this results in a positioning module as seen in this picture. At least 4 such positioning modules are required for positioning. We distinguish here between tag and anchor. The tag is located on the Alphabot and is therefore the moving part. The other 3 positioning modules are anchors that are attached to fixed positions in the room. The distances from the tag to the anchors are measured. A mathematical process called triliteration is used to calculate the position. To explain it visually, circles can be drawn around the anchors using these distances as the radius. At the point where all circles meet is the position of the tag, or the position of the Alphabot. Next up, pathfinding. From the determined position, the optimal path to a destination is found here. Obstacles are avoided, and as you can see, a distance to obstacle is also maintained since the Alphabot is somewhat wider. For pathfinding, the Alphabot uses the A-star algorithm. The area in which the Alphabot can drive is divided into a grid of 10 by 10 cm fields. Over the course of development, the algorithm has been optimized enormously. A path that took 1 second to calculate in the beginning is now calculated within 50 milliseconds. Therefore, the path can also be recalculated several times per second, so we are always on the latest state. Based on the pathfinding, a navigation system was built that follows the calculated path. Here is a visual representation using augmented reality. The position, the path, and the marking of the obstacle were projected three-dimensionally over reality. On the bottom left, this can additionally be seen in a picture-in-picture view from above. And as you can see, the Alphabot is driving to the destination while avoiding obstacles. What is also noticeable is that the Alphabot sometimes drives backwards when it's more optimal from its current orientation, so it doesn't have to turn around. Let's move on to the printed circuit board, PCB for short. Due to the high complexity of the wiring, loose contacts were very common. This made the electronics very unreliable. Therefore, a PCB was made exclusively for the ESP32 variant, whereby a large tangle of wires was reliably brought onto a compact board. First, a circuit diagram was designed. Up there are the two ESP32 boards. In the area below are the circuits for an inertial measurement unit. I will explain what that is later. And down here and up there on the right are ports for external actuators and sensors. The schematic was converted to a PCB design, and this is what the top of it looks like. The circuit board contains a so-called ICM20948 chip. This chip is the already mentioned inertial measurement unit. It contains a compass, a gyroscope, and an accelerometer. With this chip, the Alphabot can determine its own orientation very accurately. And to top it off, this chip also makes the positioning system even more accurate. That's it for the ESP32 part of my presentation. Let's move on to the Raspberry Pi variant of the Alphabot. For the Raspberry Pi variant of the Alphabot, I wrote a script that builds a Debian Linux image. The special thing about this is that the generated image can simply be written to an SD card and then used immediately in the Raspberry Pi variant of the Alphabot without any configuration effort. You don't have to bother with the installation of any frameworks or libraries. There is no need to fight with permissions or solve any other problems, because I already did that when I wrote the script. Among other things, I even found a bug in the Linux kernel and patched it. I sent a patch to a Linux kernel maintainer, and a few days later my patch was already in the main branch of the Linux kernel. By now, my changes have spread to millions of systems worldwide. The build script for the image is also used in automated tests that run on GitHub Actions. And while we're on the subject of automated testing, for automated testing of the Alphabot, an Alphabot emulator was built. This even offers other advantages in addition to automated testing. No physical Alphabot is needed to develop software for the Alphabot. So students of the programming workshop can work on the Alphabot even if they don't have access to a physical Alphabot. Furthermore, you can test whether the Alphabot stops in time in front of an obstacle without taking the risk of potentially damaging the real hardware. Those were the topics of my diploma thesis. I hope it was interesting. Thanks for watching.